Hi everybody, this is the first content video for lecture module 3 where we will be covering Earth's atmosphere. So let's go ahead and jump right in and introduce you to the content that we will be covering today in video 1 of lecture module 3. So this is the first of 3 videos that I'm going to have specifically about Earth's atmosphere. This time we're going to talk about what Earth's atmosphere is made up of, what is its composition, so what are all the gas particles that are in this room around me, what molecules and atoms are there. And then we're going to talk a little bit about how we went from the proto-Earths and then the early Earth's secondary atmosphere to this lovely nitrogen and oxygen-rich atmosphere and air that I'm breathing in this room. There was a lot of work, a lot of changes because our current atmosphere is nothing like what we expect from those volcanically outgassed secondary atmospheres that we learned about earlier in the semester. So let's go ahead and jump right in and take a look at Earth's atmosphere. So I just absolutely love this image. There are so many wonderful images of Earth and its atmosphere coming out from the International Space Station. If it was possible for me to go visit, I would absolutely sign up in a heartbeat just so I could see sunrises like this. I could see the northern and southern lights from the International Space Station and, hang out in space and be weightless. All right, so I wanted to go ahead and start our discussion with Earth's atmosphere with a picture of it because you can see how incredibly thin Earth's atmosphere is. So here you can see the surface of the Earth, and here you see space, and now you see this very, very, very thin layer of gas where it's thicker on the bottom than it is on the top. The air gets thinner the higher you go, no surprise there. But it is a very, very thin layer. If you were to go from the surface of the Earth down to the core of the Earth, you would have to travel 6,378 kilometers. If you wanted to travel from the surface of the Earth to the top of our atmosphere, defined by the Kármán line, that would be about 100 kilometers up. There is still atmospheric gas above that point. It's just that's the line where planes can no longer get mechanical lift, so they call it the top of the atmosphere. But there is still atmospheric gas above that and very, very thin layers, layers that we call like the ionosphere, the thermosphere, or the exosphere. All right, so let's go ahead and jump in and start looking at what all of this gas is made up on. And then in another video, we'll talk about the fact that you can even see different layers of our atmosphere in this image. So I know tables. Tables are always boring, but I wanted to make this one nice and big so you could see what our atmosphere is made up of. So let's go ahead and start with what our current atmosphere is. Go ahead and take yourself a nice deep breath. And what are you going to be breathing in? Well, 78% by volume of gas, 78% of what you just breathed in was nitrogen gas. Is molecular nitrogen is two nitrogen molecules represented here by these blue things that are chemically bonded together. So it's diatomic nitrogen, or sometimes called molecular nitrogen. 78% of our atmosphere. 21% of the atmosphere is oxygen, the thing that we need to stay alive. But it's only 21%. So the most abundant gas is nitrogen. The second most abundant gas is oxygen. And again, it's molecular oxygen. It's two oxygen atoms that are bound together into a molecule. So I can do some quick math in my head. 78 plus 21, that gets me to 99%. So we have 1% of other things in our atmosphere, and 0.9 of that 1% is a noble gas. Doesn't chemically interact with anything, argon. So 0.9% of the air that you breathed in, the air in this room, the air in your room, the air outside, is argon gas, and that's just an atom. And then there are trace gases. Trace gases are anything that are much less than 1%. One of the ones that we're going to be talking about a lot, and you hear about a lot, is carbon dioxide. And yes, it is a trace gas. Out of all of the air outside, it's only 0.04%. Now you could do a little bit of math, and instead of using parts per 100%, you could do parts per million. You get that's about 400 parts per million, the number that you keep hearing about when you hear people talking about climate change. Just a few decades ago, that number was closer to 0.02, or about 200 parts per million. And that's one of the reasons we talk about climate change, is that number has nearly doubled over just a short amount of time. And we have to consider the ramifications that's going to have understanding things like spectroscopy and physics. All right, another important atmospheric gas that's out there is water vapor. We know we have water vapor. We see that things get dewy in the mornings. You can form frost at night. There is water vapor in the air, and this is a highly variable thing. It can be anywhere from 0.1% to about 3% of the gas in a location. And obviously, if you're in a desert, it's going to be dry. And if you go to a tropical rainforest, there's going to be a lot more water. So that is what our atmosphere is. What you need to take away from this is that we have a nitrogen-dominated atmosphere, 78%. You should be able to recognize that number. And then the second most abundant gas is oxygen. Another thing that we have to take away from this, and it's going to be the story, it's going to be a major part of our story of how we got our atmosphere, is we have to consider how different this is from our secondary atmosphere. And remember, a secondary atmosphere, you form your protoplanet, it gets melted through radioactivity, the radioactive decay of unstable isotopes, which then heat up the planet, melt it, causes it to differentiate, and then it loses its primary atmosphere, or the terrestrial worlds do. But it's very, very hot. The early planet is very hot, quite molten, and there's this rampant period of heavy volcanism, which is going to outgas volcanic gases, a lot of that being carbon dioxide. So we expect the starting point of Earth's atmosphere, the starting point of all terrestrial planet atmospheres, a secondary atmosphere, should be about 95% carbon dioxide. That's a heck of a lot more than 0.04%. And then a smattering of other things will be in there. And let's go ahead and jump into that. So this volcanic outgassing that's going to make Earth's secondary atmosphere shortly after Earth's formation, it's going to be 95% carbon dioxide, maybe a little bit greater. What are the other gases that are in there? And these are not the gases that we see in our current atmosphere. We see things like sulfur dioxide, water vapor, which still is there, methane, and then a lot of different nitrogen compounds. Very little molecular nitrogen, but a lot of things like ammonia, NH3, nitric oxide, and other nitrogen compounds. So that's what our atmosphere was about 4.5 billion years ago. We have a whole lot of CO2, and we actually would have expected our atmosphere, the secondary atmosphere, should have been much, 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 much thicker than our current atmosphere, perhaps 80 times the mass of our current atmosphere or greater. So how do we go from this CO2-dominated, much more massive atmosphere to this thinner atmosphere that is mostly nitrogen gas and secondarily oxygen gas? Well, we can do this, and the way that this proceeds is in sort of 3 steps of evolution. Some of them are happening at the same time. In fact, the first 2 that are listed there happen at the same time, and then we add the oxygen later. So what do we have to do? We have nitrogen compounds, but not nitrogen gas. So we need to create a nitrogen atmosphere, where the nitrogen is going to be molecular nitrogen. We need to get rid of all that CO2. We have to remove it from the atmosphere and store it somewhere. And then eventually we're going to have to add in the oxygen. So let's take these one at a time, and let's start with the generating of inert. So nitrogen gas is inert. It is not chemically reactive. So once you pretty much form it, it sticks around forever. It's one of the strongest molecular bonds out there. So once you form nitrogen gas, it's going to be happy staying nitrogen gas for a very, very, very long time. So we need to create it. And how are we going to do this? We do this through a process called photodissociation. So I have tried to put together a little image over here of how photodissociation goes. But I know this is a very large word. Let's break it down. We have photo, referring to photons, referring to light, and dissociation, meaning if things are together, you're going to break them apart and send them on their separate ways. So photodissociation, another way to think about this, is breaking apart of molecules using light. So I hopefully have a little demonstration here that will help out. So early in the Earth's atmosphere, we have a lot of nitrogen compounds, represented here by a ammonia atom, where I have the nitrogen is the blue little bean bag, and then the hydrogens are the red bean bags. You can see I'm using little magnets to hold these things together. The magnets are the molecular bonds. I can go ahead and send in some light, although in the early Earth's atmosphere, this light would not just be visible, it would not be visible light, it would be ultraviolet light. So ultraviolet photons are going to get shined onto our uh, molecules of ammonia. And remember that a UV photon has very short wavelengths, has a large amount of energy per photon. In fact, the energy per photon is greater than the molecular bonds holding this atom or holding this molecule together. So whenever I shine my UV light on this, it will break apart the molecular bonds, giving us things like free nitrogen that then can get together with another free nitrogen, forming diatomic nitrogen. That did not work as well as I thought, but now you'll have two nitrogens bonded together. The hydrogen will either chemically react with something else, like since it's a very chemically reactive thing, or being hydrogen, it doesn't have a whole lot of mass, it'll drift out of the top of the atmosphere. So again, a UV photon comes along, the energy of the ultraviolet photon is stronger than the molecular bonds holding the molecule together, so that photon can break apart those molecular bonds in a process we call photodissociation, freeing up a whole bunch of nitrogens, which then can get together and will form the molecule of nitrogen, which is one of the strongest molecules out there, and it's inert, so it doesn't chemically react. So once you create it, it just sits there. So slowly, through photodissociation, we will build up more and more inert nitrogen gas, the most abundant gas in our atmosphere. So nitrogen gas, inert nitrogen gas, is created through photodissociation of the nitrogen compounds in the secondary atmosphere. Okay. Now that we have our nitrogen, what about the CO2? Sure, we can create a lot of nitrogen, but if it's just overwhelmed by such a large amount of carbon dioxide in the atmosphere, then we would not have a nitrogen-dominated atmosphere. So we have to get rid of the carbon dioxide. The way that we're going to do that is we're going to store it in Earth. And there are going to be two primary locations that we can store carbon dioxide, and the same goes for the sulfur dioxide and a few of the other gases. We have to remember that the early Earth was much, much, much hotter because it had just formed and differentiated. So that secondary atmosphere is going to be hotter, but it's going to be rapidly cooling down as the Earth cools down. And as that atmosphere cools down, all the water vapor that is in the atmosphere, the secondary atmosphere, is going to condense out and rain down onto the surface. This is how the oceans are originally formed. So as the water in the secondary atmosphere condenses to form our oceans, water does what water does, and it can go ahead and sequester, it can dissolve the carbon dioxide and the sulfur dioxide. And we're all familiar with carbon dioxide dissolved in water, because if you had a soda today, or if you've ever had a soda in your life, that soda is carbonated water, CO2 dissolved in water, so fizzy water. So as we form our oceans, the CO2 is going to go into the forming oceans. It's going to be dissolved into our oceans, removing it from our atmosphere. And now that we have CO2 in water, we can also do something else. And since we're going to now have a water cycle and rain, if you get water together with some rocks and carbon dioxide, you can drive chemistry to form carbonate rocks. So not only are we going to store CO2 into our oceans, we're also going to start forming a new type of rock, carbonates, which then will be stored into the surface of the earth and actually through plate tectonics work its way deeper down. So we are going to very slowly, over the course of about 1 billion years or so, take all the CO2, it's going to dissolve into our oceans as they form, and then we're going to form a lot of carbonate rocks, storing the CO2 in our oceans and into the surface of the earth. That will remove effectively almost all the CO2 from the atmosphere. So what are we going to have right now? We're going to have a nitrogen-dominated atmosphere. We're still lacking the oxygen. So how do we get oxygen? And this is a game of patience. So here we have a nitrogen-dominated atmosphere that's much, much thinner because we removed a lot of the carbon, we removed almost all the carbon dioxide, we dissolved it into our oceans and stored it into our surface rocks. But we don't have our oxygen. So we have to wait. And we wait, and we wait, and we wait for about 1 billion years. At about 3.5 billion years ago, life evolves. This is the starting step, but we're still not there. We got to wait some more. We have to wait about another 1 billion years for about 2.5 billion years ago when a new form of life emerged on Earth, photosynthetic life. Life that can convert light into its own energy. And in that process, what it'll do is it'll take in CO2 and expel oxygen. So photosynthetic life generates oxygen, injecting it into our atmosphere. So once we start getting photosynthetic life forming on Earth, and our main form of photosynthetic life producing oxygen in early Earth and still today is cyanobacteria. You can see modern blooms of cyanobacteria down here in this image. You can see it under a microscope right there. It's nice and green as we'd expect from photosynthetic life. And these little life forms are going to pump oxygen into our atmosphere. Now, oxygen is very chemically reactive, so we have to constantly be replenishing it. And it's going to slowly build up to the 21%, and it remains pretty stable around 21%, only a little bit of wiggle room right there. And that's because it's so reactive, so it's constantly being replenished by the photosynthetic life on Earth. And then it's being removed at the same rate through all the processes that need oxygen, like humans to breathe, and all the various chemical reactions. We see things that rust, they get oxidized, things like that. So I want to go ahead and end this video with a quick summary slide, just to put all three of those into a nice short statement. So how do we go from the secondary atmosphere that's full of carbon dioxide and other gases, including like sulfur dioxide and nitrogen compounds, to our current nitrogen-dominated atmosphere with a good bit of oxygen that we're all happy because we like to stay alive by breathing oxygen? Well, the early secondary atmosphere, we have ultraviolet light from the sun streaming in. We don't have an ozone layer really protecting us yet. So that ultraviolet radiation has no problem finding things, these nitrogen compounds represented by ammonia here. There are other ones. The light has enough energy to break apart the molecular bonds, giving us a bunch of free nitrogens, which then get together to form inert nitrogen, which slowly is going to build up on our atmosphere. As the water in our atmosphere condenses and forms our oceans, it's going to pull out the CO2 and store it into the oceans. And also we can store it into the surface by the formation of carbonate rocks, removing the CO2 from our atmosphere. Then we wait for about 1.5 or about 2-ish billion years. So about 2.5 billion years ago, we get photosynthetic life, which then pumps oxygen in and is still currently pumping oxygen into our atmosphere, leaving us with a atmosphere that's mostly nitrogen and secondarily oxygen, the atmosphere, the air that you're breathing right now. All right, so thank you for tuning into this video. We will pick up with video 2 in the next video, and we will discuss things like the layers of the atmosphere and why the sky is blue.